Okay, welcome back. This is our second video in the series. We're going to go into a bit more detail about Ohm's law. Very, very basic formula, but very, very useful for our physics. Okay, so let's revise some of the grade 10 work we did last time, where we spoke about voltage, current, and resistance. Just want to pause this video for a sec and have a look at that diagram and see if you can explain what it means. That's your chance to do that now. There we go, guys. Hope you had a quick think about that. So, what are we showing here? Current is the actual electrons that are flowing through that circuit. What's making them flow is the voltage, and what's stopping them from flowing is the resistance. These three terms are very, very closely related to each other. Okay, so what are we doing today? We're going to investigate Ohm's law, and we're going to perform calculations. This is physics. There's always going to be some calculations. It's not that hard. It's a very, very simple formula, but we've got to do it by the end of this. Okay, who was Ohm? So Georg Ohm, he's just another one of our dead white guys who did a lot of brilliant work in this area. He was a former school teacher, so you can blame school teachers for this stuff. However, he did discover Ohm's law about the relationship between voltage, current, and resistance, which is quite important. Very, very simple, but very, very important. All right, let's have a look at some experimental evidence. So we've got a graph here where we've got current on the y-axis there and voltage on the x-axis there. And you can see they form a linear relationship. All right, you can see they are directly proportional to each other. So we would say that the current is proportional to the voltage. All right, and if you look at these graphs, they're linear graphs. What do we do when we get a linear graph in physics? We find the gradient. So if we want to find the gradient of either of these lines, like that red one there, it tells us there that the gradient, for example, on this one would be 20. And what it's actually telling us is that this is a measure of the resistance. So if you did an experiment with a 20 ohm resistor, like that one there, and you measured the current and the voltage for different voltages and different currents, you should get this linear relationship. When you find the gradient of that, you'll find the gradient is 20, hence the resistance is 20 ohms. And that's what Ohm has discovered. Same with the different one down here, different resistor was used, so there's a different gradient used. Can you see the experimental relationship here? We take some data on voltage and current, measure it, graph it, see it's linear. We want to find the gradient of that, and what does that gradient tell us? And you look at your equipment and you realise you used a 40 ohm resistor, therefore the relationship is quite straightforward. If we write that out mathematically now a little bit more formally, we'll get this one here. Voltage equals current times resistance. So V equals IR. A very, very important formula, very, very basic. So V is voltage measured in volts and its symbol is V. I is current measured in amps, its symbol is an A. Resistance is measured in ohms and the symbol is omega. Right, why have I got those two pictures down the bottom there? You may recall this guy on the left here is Will Smith from I Am Legend, which was a remake of an older movie, which was called The Omega Man, which is Charlton Heston, which is even way back before my time, probably before your parents' time, who knows. It's a very old movie, obviously based on a book, because most good movies are, but it was originally called The Omega Man. Maybe you might want to check it out one day. Right, so Ohm's law. Ohm's law is applied to a circuit, part of a circuit, or even an individual component of a circuit. Now, a few things about circuits that I haven't discussed. So in this particular scenario here, we have a 9-volt battery, and you can see we've got the negative side and the positive side. And in blue there, I've shown where the electrons are actually flowing. They flow out to the right-hand side there, down through resistor A, through resistor B and C, and then back to the battery again. This is electron flow. But now the problem here is when humans first started describing electricity, back in Ben Franklin type times, a long time ago, more dead white guys, yeah. We originally thought electricity was a flow of positive current. So it came out of the positive side of the battery because there was more of it and went around to the negative side of the battery because there was less of it. Now we've since found that that's wrong. It's actually electrons because they're much, much smaller and they're the ones that flow around the circuit. But the difference here is we still refer to conventional current. which is what current is. So that's this one here. The conventional current flows from the positive to the negative around a circuit. Now I must stress, in this scenario, in electricity circuits, conventional current does not exist. The positive protons do not move because they're so much bigger than the electrons, 1,800 times. Conventional current doesn't exist in our circuits, but we still refer to current as conventional current because that's what our laws and relationships are all built around. Okay? I know it doesn't make sense, but that's what we do. Electrons are what actually flow. It is opposite to conventional current. We do talk about positive current flowing. For example, if we're talking about nuclear radiation and we're talking about an alpha particle, which is a helium nuclei, which is a positively charged particle, that could flow. That would be a positive current, but that's a very special example. When we refer to current, we're referring to conventional current, which is which way would a positive charge flow if it could flow in this circuit. That obviously doesn't exist because it's electrons that flow and the electron flow is in the opposite direction. Unless you're told otherwise, conventional current is what we're always talking about, which doesn't exist. Right, so when we do our circuit analysis, we can analyse using Ohm's law different components of this circuit. We've got some resistances, we've got the battery, we can look at the total resistance in the circuit, the total current, and the voltage used up by the individual parts of the circuit. Now, how do we work out the resistance? This example I've got here is a simple series circuit where everything is all in one big long line. So all the current's going through every component. And to work out the resistance in this circuit, very simple formula, we just add up all the individual resistances in each part of the circuit. They all just add up together. Resistor 1 plus resistor 2, so on, so on, so on to the final resistor, Rn, I've called that one. Make sure you're using standard units, which are ohms. Don't use micro ohms or anything other thing like that. We're just using ohms. So, question here is, what would be the resistance of this circuit shown? I want to add up all the individual resistances I have, and that will give me my answer. Here's a nice way to set it out. Resistance total equals R1 plus R2 plus R3, or A plus B plus C. That's that line there. Plug in my numbers and add them all together. 3 plus 10 plus 5 is 18 ohms. When you're doing your final exams at the end of grade 12 and so on, this is a good habit to get into. Now, I've lined up my equal signs because that's how we neatly write out mathematics, much like we write a capital at the start of a sentence and a full stop at the end of a sentence. You probably don't question that. That's how we do it in English. But when it comes to doing these sorts of questions for your grade 12 exam, there's usually a mark for writing down the formula, a mark for putting your numbers in and doing the working out. That's what we refer to as mathematical reasoning, and a mark for the actual right answer. So that would be a 3-mark question. Write each 3 parts and you'll be good as gold. Right, next question. What would be the total current in the this circuit shown? So we know the total resistance. We found that on the previous slide. We know that the battery is 9 volts because it says up there. My resistance is 18 ohms. I'm just going to use V equals IR to find the total current in this entire circuit. So again, this is probably a 3-mark sort of example. Write the formula down, V equals IR. Now I've rearranged it. Writing down the formula shows that you understand this is about an Ohm's law question, and that's usually where there's a mark allocated in your final grade 12 exam. Your mathematical reasoning is something, this bit in the middle here, for putting the numbers in the right spot, in the right sort of form, and then a mark for the last part. So it's 9 volts divided by 18 ohms is half an amp. Pretty straightforward. Now, remember in the previous video, I spoke about this little image here where I showed that the battery has potential energy that it puts in the circuit, and there's this rise here, and that energy is used, and we say the potential drops as it goes through the load element. In this particular scenario here, I've got my 9 volts in my battery, and it's going to be shared, that energy is going to be shared between this resistor, this guy, and this one over here. All right, so now I particularly want to know what is the voltage used up by the 10 ohm resistor. I'm going to use Ohm's law, so let's think about what we know. I want to know the voltage in that resistor, which is that first term there. I know the resistance because it says it's 10 ohms, and I know the total current going through the circuit because we just worked it out in the last question, half an amp. So I can write down my vehicle's IR. I know that the total current in the circuit is half an amp. I know that this way is a 10 amp resistor because it told me there. 0.5 times 10 is 5 volts. You can do the same question now and you can work out how much voltage is used by this guy here and how much is used by this guy here. But what we know is this. We know that there's a total 9 volts to share. If this 10 ohm resistor is using 5 volts, there's only 4 volts left. 9 minus 5 is 4 volts to be shared between this one here and this one here. Okay? Plug it into the formula and you'll work it out. Okay, what do we have to have a look at with this question here? Let's see if we can apply some of our knowledge. Can we describe how a lie detector test works? Now, lie detectors are not scientifically accurate. There is no actual proof, despite what the movies tell you, that these things are scientifically accurate. It is possible for someone to beat a lie detector test and be completely lying, but control their heart rate and so on, and still appear to not be lying. And the opposite of that is also true. An innocent person could be very, very sweaty and worried and anxious that they're being interviewed by the police and they don't normally talk to the police, and hence return a false positive. So there is no scientific evidence that they actually work. But how are they actually designed to work? Think about the two images there where we have sensors and so on placed on people's skin to measure their heart rate and so on and things like that. But the thinking is the more stressed you are because you're lying, the more you're going to be anxious and start sweating, which would change the conductivity of your skin. Let's think of V equals IR. If the conductivity of your skin reduces, the resistance is actually reducing. So mathematically, if my voltage is constant, then mathematically the current would increase because it's I times R. So if R gets smaller, I has to get bigger for a particular voltage that's given. The machine can sense that there's more current flowing, and hence that shows up on as a lie. Okay, nice little video there for you to watch. You can check that guy out, do a little bit more work on this one. And there's a worksheet in the OneDrive that I've saved for you to have a look at, but you should be able to go and have a look at that one and do some calculations on this stuff. Okay, thanks for coming, guys. It's been fun, really fun, and I'll see you next time.